Okay, morning everybody. So it's my pleasure to introduce Franz Tuchen. Philip did his undergraduate, master's and PhD degrees in Germany at the University of Kiel in North Germany. He worked with Joke Lübecker and Peter Brandt. And he's been interested in equatorial and tropical dynamics throughout that time. Since 3.5 years he's been here in Miami. He's been on a National Research Council Postdoctoral Associate Award, working at NOAA-AOML with Reneles Perez and Greg Holtz. So welcome, Philip.
Thanks. Okay. Yeah, thanks Lisa for the introduction. Like Lisa said, I'm Franz Philipp Tuchen. I usually go by my second name, so if you call me Franz Philipp, you're probably my parents and I did something wrong. I usually really go by Philip, so that's fine. First of all, thanks for inviting me to give this presentation. I think that's, for me, it's a great accomplishment and also a great honor already. And I would like to talk today about how my research has advanced our understanding of equatorial ocean dynamics and how in the future we can even improve this understanding further. And I would like to start with an overview of just the motivation of why we should care about the equatorial Atlantic. So showing here is a figure of sea surface temperature in the tropical Atlantic. It's like a regular or typical Northern Hemisphere summer day. And there's a lot going on at different scales on this figure. So on the large scale we see there's this tongue of cold water in the equatorial Atlantic, which we call the equatorial cold tongue. So it develops usually in the summer. And every few years this cold tongue of water is significantly less pronounced. It's like a heat wave. And in these periods, or in these years, we typically observe heavy rainfall over the northeast of South America. We also observe increased rainfall over the Gulf of Guinea. On the other side, we observe droughts in the Sahel region, and we even see tropical cyclones or increased tropical cyclone genesis in the eastern Atlantic. So besides the local impacts, there's also an impact on the other ocean basins from the Atlantic to the Pacific Ocean, through atmospheric teleconnections, and also to the Indian Ocean. So overall, the equatorial Atlantic plays a huge role for the large-scale climate variability. If we zoom in a little bit on the mesoscale, we see these wave-like patterns at the northern edge of the cold tongue. So these are the signatures of tropical instability waves. And they cause, for example, a meridional exchange of heat. So they bring the colder waters from the equator northward and the warmer waters of the equator towards the equator. So these mesoscale features, they can even have an upscale impact on the cold tongue in the end. And if we zoom in even further, we observe that these instability waves very sharp fronts of sea surface temperature. And then coming into the submesoscale, small scale processes, there's a lot going on these scales. You see vertical mixing, very local upwelling, and also biogeochemical variability at these fronts. So I'm interested in all these different scales, and I'm trying to make the point today, or trying to show you what we have learned already from at these different scales and how we can improve our understanding with future research. So just let me provide you with a very brief outline for today. So I'm going to talk a little bit about my path so far, my academic experience and my professional experience. Then I'm going to give you a background on the equatorial Atlantic Ocean, what we need to know in a very, very fast way, and then how we are currently observing these features with our observing system in place. And then I'm going to provide you with 3 examples on how my research has advanced our understanding from large-scale Atlantic new events to the mesoscale, tropical instability waves, and then towards the small scales where we observe these physical biogeochemical interactions. And in the end, just a few slides on what I think are important open research questions to address and how we can address them in future research. Okay, so starting with a very short introduction. So like Lisa said, I did my bachelor in Kiel in Germany, finishing my bachelor in 2013 with a thesis on the impact of wind stress on the Atlantic meridional overturning circulation, supervised by Mochi Latif. I then stayed at the AOML, working on a thesis with Peter Brandt, turning more towards physical oceanography so a thesis on interseason variability of the Equatorial Atlantic Ocean. And then I was lucky I could stay. I was offered to work as a doctoral researcher with the topic on more subtropical dynamics of the Atlantic subtropical cells, mean state and variability from an observational perspective. I stayed for 1 more year at GEOMA. I was working on a paper on tropical AMOC pathways and combining a data set on equatorial velocity data. So we're going to talk more about especially this data set later. And then I came to Miami in early 2022 on a fellowship by the NRC. So I focused in this fellowship on the long-term variations of tropical instability waves. I'm going to present more on this, on our research results later on. And then last year I made the switch to becoming a CIMAS postdoc, and since then I've been working mostly on Equatorial Atlantic, also Pacific variability and extreme events, mostly in the Atlantic Ocean. And I would say my research interests are very broad, so I'm interested in upper ocean dynamics and deep ocean variability. I'm interested in scales from diurnal cycle to multi-decadal trends. I did some detour to the Pacific Ocean, and I mostly use observational data. So I mostly use in situ observations from moorings, from shipboard measurements, and then also combine them with satellite observations. Okay, so brief background information on the Equatorial Atlantic. So it always starts with the incoming solar radiation, which is maximum at the equator, on average at least. So this means that on the equator, the warm air rises and forms these clouds and these rain bands along the tropics. So at the top of the troposphere, what happens is that the air diverges to the poles, and this means that there must be some convergence of air at the surface. But at the surface, in general, the equatorward winds, they diverge or they deflect towards the west due to the Coriolis force. So in the end, we end up with mostly westerlies, westward winds or easterlies on the equator. This is important for the zonal currents on the equator, which I will show you in a few slides. First of all, we call this convergence of air at the surface the intertropical convergence zone, the ITZ. You can see this here in the two different figures showing rainfall from January and rainfall for July. So these rain bands along the equator, or just north of the equator, this is what we call the ITCZ. And you can see this differences between where the ITZ sits in the January and where it is in the July. There's a difference in amplitude, so it's stronger in July, and it's also further north in July. And this vertical or meridional migration has implications for a lot of different parameters. It sets the seasonal cycle in the Atlantic. The surface winds, they change accordingly through the year, and it has impact on the surface currents, the equatorial upwelling, and also the rainfall pattern. So, like I said, in the equator, we have mostly westward winds or easterlies, and at least on the equator, this has a direct impact, causing westward currents along the equator. So most prominently these two bands, which are the northern and the southern branches of the South Equatorial Current, SEC. So these currents are pretty strong, one of the strongest currents in the tropics, but there's even stronger currents on the western boundary, mostly the North Pacific current, which is a pathway for the AMOC, which transports the water from the south through the tropics into the North Atlantic at shallow depths. So overall, we see there are two different, there's a combination of the equatorial zonal circulation system and the western boundary circulation system. So overall, the Equatorial Atlantic is really a hotspot for different circulation systems. We also see that due to the strength and the different directions of the zonal currents towards the north, we end up with regions with a lot of meridional shear in between them. And that's going to be important for instability processes when we talk about tropical instability waves, for example. One important implication of the zonal current system is how it is shaping the distribution of dissolved oxygen, which is shown here in the color shadings. So blue meaning less oxygen and red colors meaning more oxygen. And you can see these oxygen minimum zones north and south of the equator, but you can see that especially along the equator, and especially the equatorial undercurrent, the EOC, which is one of the strongest currents in the tropics really, that is really shaping the distribution because it brings the oxygen-rich waters from the western Atlantic towards the east and helps ventilating these regions. So you can also see that compared to the previous slide, the equatorial current system is much more complicated than maybe made you believe from the previous slide. There's a lot of different currents at different depths and at different directions going on, but of course, mostly west to east or east to west currents. So, like I said, the equatorial undercurrent is one of the strongest currents. It roundabout transports 100 times as much water as the Amazon River, for example. And so it's worth just to mention how it is formed on one slide here. So if you look at the equatorial Atlantic from east to west, and then from the upper 300 meters roundabout, again, like I mentioned, we have the easterly trade winds on the surface. And this means these trade winds, they cause some piling up of waters from the east to the west. And this means we have higher pressure in the west than in the east. So we have a pressure gradient in the zonal direction. On the equator, the zonal pressure gradient has to be balanced by a zonal flow. So there's no Coriolis force, there's no real geostrophy. So there's only the pressure gradient, the zonal pressure gradient, and zonal velocity. So that means at thermocline level over here, the equatorial undercurrent develops, which is then basically balancing the pressure gradient at the surface or at the upper ocean. So the undercurrent is deepest and strongest in the west, and then it shoals towards the east and becoming weaker due to recirculations along the way. And you can also think of this as some kind of zonal overturning circulation, right? So we have, in the end, we bring surface waters to the west, so the warm waters to the west, and then the colder waters bringing them more to the surface in the east. So there's also some warm to cold zonal gradients just by the zonal by the trade winds in the end. And this is most pronounced, of course, when the winds and the currents are also most pronounced. So showing you here is the sea surface temperature distribution for spring and summer in the colors, and then the arrows show the winds. And the difference between northern hemisphere spring and northern hemisphere summer is quite substantial, especially in this equatorial region, where again the equatorial cold tongue develops in the summer. And this is due to two reasons basically. So on the one side, as I mentioned on the slide before, the winds transport the warmer waters to the west and then bringing colder waters up in the east. But then also, a little away from the equator, the westward currents, they deflect to the north and to the south. And this is what we call the Ekman divergence about the equator, which implies there's upwelling on the equator, bringing colder waters to balance the divergence at the surface. And especially this region here in the equatorial Atlantic, this is what we call the Atlantic 3 region, which is becoming more important in the next few slides when we talk about interannual variations of this region. Because usually in this region we have a seasonal cycle that looks something like this in the black line here. So we have maximum temperatures in the spring, and then we have minimum temperatures in the summer. This is the cold tongue again. And then increasing temperatures again towards the end of the year. But then if we look at monthly data, we often see anomalies from that climatological cycle. So warm anomalies in red, and blue anomalies in cold anomalies in blue. And if we look at the last 30-something years and just look at the anomalies for every month, we end up with something that is looking like this. So we have these phases of extreme warm events and extreme cold events, which are in the most extreme phase, or in their most extreme extent, called Atlantic Niños and Atlantic Niña events. And we became very interested in these events more recently, because as you can see, there have been a few recent events lately, after a long period of rather absence of Atlantic Niño events. So there was a strong warm event late 2019, and then a very strong Atlantic Niño event in 2021, which is often called the Super Atlantic Niño. And then just recently, last year, we had record heat in the Atlantic region, and also a record drop in sea surface temperature anomalies. So this matter has really become more interesting in understanding these events in more recent time. Because we already know some ways or some mechanisms how these Atlantic Indio events are generated. In a recent or quite recent review study by Joko et al., they mentioned 5 different mechanisms that can lead to Atlantic Indio events. So on the one side, there's the Biagness feedback that involves changes in the trade winds, followed by changes in equatorial wave, and then thermocline adjustment in the subsurface, so a whole series of ASC interaction processes. There's also the option of advection of heat off the equator towards the equator. There's the possibility that off-equatorial waves reflect at the western boundary and turn into equatorial waves, and then set or initiate these warm events. There's also the theoretical option, at least, of just interior ocean variability, these long-term variations of the deep circulation that can lead to energy propagation towards the surface. And then there are thermodynamic processes through heat flux at the surface that can lead to such events. And lately, since that review paper...
I have one question.
Yeah, sure.
So how come the processes that's happening in the Pacific are not included here?
They are indirectly included. So what the Pacific impacts the Atlantic is through the change in the water circulation to atmospheric teleconnections. And this will lead to either off-equatorial or equatorial wave excitation, basically. So it's indirectly included here. I will mention also more the El Niño, because that's one way we found, one reason why the record event in 2024 happened. That's due to El Niño. Right, so since that review paper, we were actually able to add 2 more recipes for driving Atlantic Niño events. So the 2021 Atlantic Niño, for example, was forced by an atmospheric extension of the Melon-Joule oscillation into the Atlantic Ocean. And then the last year was strongly impacted by the decaying 2023-2024 Atlantic Niño, El Niño event in the Pacific Ocean. So I'm going to mention this in a few slides. And just to mention the impacts of Atlantic Niño, I mentioned in the beginning, they have a huge impact on rainfall patterns on the surrounding continents. They also just recently were found to have an impact on tropical cyclone genesis in the eastern Atlantic. So just very briefly, during positive Atlantic 3 events, which is basically Atlantic Niño events, the number of major hurricanes is significantly higher than during Atlantic linear events, for example, or during neutral conditions. And you can see this also from a spatial point of view. In the eastern Atlantic, this is where tropical cyclone genesis is more likely during Atlantic Niño events. And these events, or these tropical cyclones near Cape Verde, these sometimes turn into one of the strongest kinds of hurricanes and most destructive hurricanes. So it's really important to better understand what is driving these Atlantic Niños, because in the end, better understanding of that could help to better predict these events, and then theoretically also help with tropical cyclone forecasts. Okay, coming a bit more into the mesoscale again for the tropical instability waves. I mentioned the cold tongue in the Equatorial Atlantic, and I mentioned these warm cusps, cold cusps and warm troughs, which are the signatures of tropical instability waves in the Equatorial Atlantic in SST. So I mentioned that these instability waves, on the one side, they drive meridional heat exchange between the equator and the off-equatorial region. They also cause shear-driven vertical mixing. So this is causing cooling in the upper ocean. And this means that at least on the equator, tropical instability waves have counteracting effects based on advection and mixing. So there's mixing induced cooling and advection induced warming on the equator. These instability waves, they can be found in the Pacific and the Atlantic Ocean. They usually appear as these westward propagating waves of the equatorial cold tongue front. They have spatial scales of a few hundreds of kilometers, And if you observe them at one location, it takes about 20 to 50 days for one wave, to pass for one wave. So the wave period is about 20 to 50 days, which we usually call the interseasonal period range. And actually, you can see, this is now SST, but you can see the impact of tropical instability waves in almost every variable that you can think of. So for all these variables, physical, biological, chemical, it's the number one reason for interseasonal variability in this region is always tropical instability waves. There are two ways how tropical instability waves can be generated. So on the one side, there's the barotropic energy conversion term, which is basically saying we have the meridional shear of a zonal current system. So between these strong zonal currents, meridional shear develops, most pronounced during the summer. So this is one part of one term of the barotropic energy conversion, which is basically describing how mean kinetic energy is converted into eddy kinetic energy, so from the background currents into the fluctuations. So it's either through the meridional shear of the zonal currents or through high frequency current fluctuations. The other way, or the most prominent other way, is baroclinic energy conversion, and that involves usually sharp density gradients or fluctuations at density gradients, as we also usually see at these very sharp sea surface temperature gradients at the cold time front. But I'm going to mention that baroclinic energy conversion is much harder to observe. As you can see, it involves knowledge of vertical velocity fluctuations, density fluctuations. It's a little easier, not easy, but a little easier to observe barotropic energy conversion. Okay, this brings me to the existing model biases that we still observe in the Equatorial Atlantic, which is still a very big problem. So in both CIMAS 5 and CIMAS 6 models, and historically, the Equatorial Atlantic, this shows this warm bias when you compare it to observations. This is not just a warm bias, but it's also a bias or an underestimation of the steady trade winds and an overestimation of the rainfall in this region. And there has been some progress, or some of these biases were ascribed to atmospheric processes, but ocean processes, they still play a huge role. There have been some advances with increasing the resolution of models, but still these models show a bias. And even not just in the CIMAS 5, CIMAS 6 models that are used, for example, for the IPCC report for climate predictions and projections, also had very high state-of-the-art storm resolving models, like the ICON and the FISA model. For example, in this case, the equatorial circulation is not well represented, even when you change, for example, the mixing parameterization. So in this study by Bastien et al., they found that using two models, changing the mixing parameterization between these models, it does fix it in one model, but it didn't fix it in the other model. So there's even a model dependency on how parameterizations can improve the representation of what we actually observe. So yeah, I think in summary there's still a lot to do. And I picked 3 quotes from recent papers to just highlight these challenges at the moment. So just from the previous slide, the Bastien et al. Study, they mentioned that in light of the numerous studies that have been conducted on this topic, so the model biases, we conclude that the tropical Atlantic remains a challenging region for ocean models. Then in a recent review paper by Zero et al. On mesoscale air-sea interaction, they say that the identified common biases and mesoscale air-sea interaction in such climate models in turn guide the sampling strategy of observing systems and process studies. And I really read this as a mission for observational oceanographers to first of all acknowledge these existing model biases, but then try to address these model biases by adjusting or tailoring your observing systems to these processes to better understand them, and also to tailor or to design dedicated process studies to work on these biases. And this is also reflected in the last statement by Clayson et al. They say additional value could be extracted from future studies if their findings were a source for a dedicated pipeline, wherein advances in understanding from observations systematically flow toward model development and prediction improvement. Again, I think that's something I really identify with. It has to be a joint effort between observations and model improvement between the observational oceanographers and the modeling community. So the way we are currently observing the Atlantic is mainly through the Tropical Atlantic Observing System, TAOS array, and this is including a variety of different observing platforms coming from Pirata moored surface buoys in the red squares, the occasional subsurface moorings in the equatorial and subtropical Atlantic. We have repeat ship cruises, we have ghost ship lines, we have XVT lines, we have surface drifters, we have Argo floats. There's also, of course, a light observation of the surface, so it's a huge array in general. And especially the Pirata moored surface array has been really the backbone of this observing system for almost 30 years now. It has led to more than 400 publications using their data, and has really advanced our understanding of the equatorial and the tropical Atlantic in general. And I want to highlight here one observing system, because I think it's one of the most successful stories of the observing system, which is including data from the Pirata buoy and the subsurface mooring, and it led to one of the longest full depth time series of velocity data worldwide. And this time series is shown in this figure here. So it shows the zonal velocity data from surface to bottom since 2001 and until the last update in 2023. So I've been in charge of this time series since I started working with observational oceanography in 2014. The time series consists of a variety of different instruments. So in the top 1,000 meters, we have 2 ACPs. We have a moored profiler for the deep ocean velocity, and then we have current meters at varying depths. So we always adjust the setup of the mooring to generate the best outcome. Especially in the zonal velocity time series, we see the main features at the near surface, the equatorial currents and its variations over time. And we see the downward propagating signals here, which are called equatorial deep jets. So it's a very unique time series in which you can actually see these deep jets, and in which you can see the time, or how long it takes for one of these jets to propagate all the way down. So you need these long time series to fully resolve the temporal scale of these long-term deep ocean circulation features. Like I mentioned, I started working on this data set in 2014, assembling all the data that was already available, and then constantly updating the data every cruise that we went out over the last 10 plus years. And we just recently came back in February this year, so very soon I'm hoping that there's going to be an update. We have the data, but very soon hopefully there will be an update. Okay, so now I'm just focusing on the examples that I want to mention, how my research actually improved our understanding at these different scales. I'm starting with the Atlantic Nino. So as an overview, what we found is that we added one more driver of Atlantic Nino events, which is the Julian oscillation in case of the 2021 Atlantic Nino. Then I was able to attribute the equatorial Atlantic variability of last year to the decaying phase of the last El Nino event. And then also I was able to analyze in the case of the very strong 2021 Atlantic Nino, how it impacts equatorial currents and tropical instability waves. So starting with the first bullet point, the super Atlantic Nino in 2021, which was described by very strong SST anomalies in the equatorial Atlantic, up to 1 degree over this 3-month period of time. It caused heavy rainfall over the Western African region and the Northeast Brazil or Northeast South American region for most of the Northern Hemisphere summer in 2021. And it was interesting because there were actually 2 processes at work that led to the event. So first of all, there was a off-equatorial Rossby wave that reflected at the western boundary as an equatorial Kelvin wave. So that itself is nothing unusual. What was unusual was that this relatively small signal was heavily reinforced by a local process in the central Atlantic. And we could show that this westerly wind burst that caused a huge intensification of the Kelvin wave, that is shown here by calculating the Kelvin wave forcing index just based on wind anomalies. So just at the right time and at the right location, this wind burst reinforced the existing Kelvin wave and caused this huge event with a huge thermocline deepening and a huge reaction in SST. So we were able to actually attribute this wind burst to the May-June oscillation that was unusually strong over the Atlantic. So the May-June oscillation is a known driver for El Nino events in the Pacific, but it hasn't been mentioned at all for the Atlantic region. So we could show that this is actually playing a role in the Atlantic as well. Okay. And then very recently, the Equatorial Atlantic experienced a year full of extremes last year. So in the spring of last year, the Equatorial Atlantic showed for the first time in this Atlantic 3 region monthly mean temperatures of more than 30 degrees Celsius for 2 months in a row. And we were able to show that this is actually caused by a connection to the decaying El Nino phase. So in the late phase of an El Nino, the El Nino causes subsidence over South America, so downward winds over South America, which then leads to westerly winds in the western Equatorial Atlantic. And that set up a huge Kelvin wave again, which caused even further deepening of the thermocline in the Equatorial Atlantic. So a record heat event in the boreal spring. And what was interesting about it, that from this record heat event in the spring, there was a huge drop in SST actually towards the summer. So a drop by almost 6 degrees Celsius, whereas usually you have a drop of 3 to 4 degrees from spring to summer. And this was actually caused by a very unique series of wave propagation, wave reflection, and reinforcement. So using satellite altimetry data at the equator and off the equator, we were able to show that this very strong Kelvin wave that you can see here, propagating west to east, was reflected at the eastern boundary and across the equator, across the Equatorial Atlantic again, and was even another time reflected at the western boundary again. And this caused some interaction with the first of all, right. So this whole reflection of equatorial waves then led to the termination of the cold event that we see also in this negative sea level anomalies over here. So we could show that this very unique series or sequence of equatorial waves led to the observed equatorial Atlantic variability, and it all started with this huge Kelvin wave caused by El Nino. Besides the reasons for El Nino, I'm also interested in the impacts on, in this case, equatorial currents and tropical instability waves. And again, the 2021 El Nino was a perfect example of how it impacts the equatorial Atlantic ocean dynamics. So usually, if you remember, the zonal currents look something like this with these strong westward currents near the equator. But in 2021, the anomalies of zonal velocity during the onset of the El Nino showed very strong positive zonal velocity anomalies, meaning a huge reduction of the westward surface currents. And this is confirmed by data shown here at the Pirata buoys at the equator and also at 4 North. We also found that during this event, from subsurface buoys, or from subsurface mooring data and velocity data, and not using here the meridional velocity data for 3 years, we could find that there's a strong reduction in tropical instability wave activity. So usually you see these strong fluctuations near the surface and meridional velocities, so northward, southward velocities. You see them in 2020, you see them in 2022, but they are basically absent in 2021. And this is also shown by something like, well, this is resembling an activity index for tropical instability waves. So again, huge absence of tropical instability wave activity during an Atlantic Nino event. And this has to do with a combination of reduced shear between the ocean currents and reduced high frequency fluctuations. So we could show that the barotropic energy conversion term was hugely reduced. Okay, and this brings me to advances at the mesoscale on tropical instability waves. So in my research, I was able to characterize the seasonal cycle of Atlantic TRWs in great detail. I was able to show that tropical instability waves are also a source for equatorial waves, and they have an impact on the deep equatorial circulation through this wave excitation. And I also showed that there's a multi-decadal long-term intensification of these waves, but on top of that, very strong interannual variability of Atlantic tropical instability waves. So the season cycle is shown here based on mood velocity data, so we can clearly see how during the boreal summer, when the winds and the currents are the strongest, tropical instability waves in terms of velocity data are also the strongest. And we also show, I could also show this from a spatial point of view using satellite data in sea surface temperature and sea level anomaly, that especially in this region between 30 west and 10 west and north of the equator, tropical instability waves have their strongest, are strongest during June, July, and August. But there are fine differences between different parameters. So it's not always the same latitude, not always the same range, not always the same month, but in very general, it's in the northern hemisphere summer, north of the equator, between 30 west and 10 west. Okay, yeah, you remember the time series that I showed you? This was for the zonal velocity component. And in case you were wondering, of course, we also have the same data for meridional velocity. But the reason we always show the zonal velocity is because it looks much nicer. It's very different in meridional velocity because there are different signals at different time scales. In the zonal velocity, we have signals that vary over years, months, or multiple years. In the meridional velocity, it's really intraseasonal signals. So you can see it looks very different. It looks almost noisy. You have to zoom in to this time series to actually see some nice features. And when you do, you see these downward propagating signals. So you see an upward phase propagation of the signal, but a downward propagation of the energy. And so at this depth, these signals, they cannot really be associated anymore with tropical instability waves, right? So tropical instability waves are forced waves near the surface, but at this depth, there must be something else going on. And the best candidate for that is equatorial waves. So there are, just very in general, there are 4 different kinds of equatorial waves. And they are all defined by their zonal characteristics to the wave number and by their frequency, so in time. So at very high frequencies, there are gravity waves. At positive wave numbers, Kelvin waves. Then at basically all frequencies and mostly at negative wave numbers, there are Yanai waves or mixed Rossby gravity waves. And then at lower frequencies and negative wave numbers, there are Rossby waves. So we were trying to attribute our observed signal to one of these waves. And it's not easy to do this from one mooring location because you have no information about the zonal extent, right? So the only axis that you can get information out is the frequency or the time dimension. We were able to use one trick because we know that Kelvin waves, they only have a zonal component. So we don't expect them to have any impact on our meridional velocity signal. So we can exclude Kelvin waves as one reason, which means a window opens on the frequency range where only Yanai waves exist, right? So there's between the maximum frequency of Rossby waves and the minimum frequency of gravity waves, there's a window where only Yanai waves exist. And I was able to show with something called like a mode decomposition analysis that it's actually very much the Yanai waves that cause these signals in the meridional velocity. And this was the first time that these deep ocean waves were actually confirmed by observations, and we were able to show that tropical instability waves near the surface are a source for these intraseasonal variations. And in a more schematic way, you can think of these the way that these waves propagate the energy downwards along these beams. So near the surface, they get excited, and then they propagate the energy downward and eastward into the deep ocean. And it takes several months before they reach the deep ocean, really. And this is important because at depth, these waves interact with the deep zonal circulation or with the deep equatorial zonal currents. And this leads to something that is coming from a very old textbook by Adrian Gill, and this is called the banana-shaped eddy. So if you think of a wave from an horizontal point of view, and you think of zonal currents that distort this wave, you actually create some momentum transfer into the currents, right? So this was done in a paper by Greatbatch et al., where we could actually and confirm what the models show using our mood observations. We were able to show that this term is actually contributing to maintaining the deep ocean circulation. That's a powerful tool to confirm model simulations with actual in situ observations. Okay, coming to what I also did after that was that I looked at the long-term trends of tropic instability waves, and you can see the increases of tropic instability waves in SST and in sea level anomaly in the very same region where they also usually peak, and it's a very nice long-term intensification of both waves, of tropic instability waves in both parameters, so more than 40% or 26% respectively. So what I also found was when I did this study in 2022, at the beginning I didn't have the data for 2021, so I even had higher trends, 48 and even 35% for sea level anomaly. But then as the year progressed and we actually got the data for 2021, these trends were in the end significantly reduced. And this is again just showing you how these interannual variations of tropic instability waves, they really have an impact on the long-term trends. So we need these long time series in order to actually see these emerging signals on longer time scales. The reason for the long-term intensification is mostly the barotropic energy conversion that you can see here on mean in a band between the NECC and the NSCC. And in the same region, we see a significant increase of barotropic energy conversion. And it's interestingly, not that the shear is increasing, but the high frequency current fluctuations are the one term that is increasing. And there are impacts of a long-term intensification of tropic instability waves. I mentioned the meridional exchange of heat. There's cooling north of the equator usually and warming on the equator. And this cooling-warming pattern has increased by 74% or even 85% over the last 30 years. So again, can have upscale impacts on the large scale distribution of heat. Okay, and then lastly I want to mention a few very recent advances on physical biogeochemical interactions. So during the 2021 event, I was able to show that these events have a significant impact on the surface chlorophyll concentration. And then even more recently, we could show that these both extreme events and short-term tropic instability waves have an impact on carbon export in the end. So again, the super Atlantic India in 2021, shown here in a Hoffman diagram, that had a huge impact also on this, reducing the surface chlorophyll concentration in the same time of the year. And this is very interesting because at the same time we actually had a BGC Argo float out deployed in July 2021, and it was equipped with an UVP, an underwater vision profiler. So this instrument takes very high frequency pictures of an illuminated volume in the ocean, and then it counts the particles within this volume. So in the end you get the particle concentration for different size classes at every depth, and because this is an Argo float, we have vertical profiles and we can actually calculate carbon flux and carbon export. And we were actually able to keep this Argo float on the equator because we used different depths for the parking of the Argo float based on the zone currents that are going in different directions. So we're managing quite well to keep this float on the equator, and we actually recovered it in the end by another cruise. And the data is great. The data shows you that in these 5 different size classes for 5 different morphotypes of marine snow, so particles in the ocean, we see, especially in the small dense particle size, these 2 events of carbon export from near the surface down into the deep ocean. And this is mainly due to the variability of upwelling, so cooling or thermocline shoaling during upwelling, which is then causing the particles to sink through the thermocline or below the thermocline. But then on shorter time scales, there are also interseasonal variations by tropic instability waves, which can cause local upwelling and contribute to the export events. So, and you can see interestingly that somehow the winter event was stronger than the summer event, whereas you would think upwelling is stronger in the summer. But again, this is the Atlantic India year, so that's when we had a huge reduction of the cold term, less upwelling, So this is why the winter event appears stronger than the summer event. And this means we need more observations. So we did this by including UVPs into moorings to get long-term time series, so we can actually characterize the seasonal cycle and interannual variations from a more local point of view. And we've done so on some moorings on the equator, different depths on the equator, and also further moorings in the future. Okay, so I hope I'm finishing now on time with just a few points on what's up for the future and what I think are important questions to address. So first of all, I think what has to be done in the future is we have to better understand these small-scale processes. There are so many processes like local mixing, upwelling, deep cycle turbulence, these physical BGC interactions. We need to better understand them, observe them, understand them, and then understand how they interact or how they impact the mesoscale and even large scale. Because there are model observations, model studies that show that these small scale features, they have an impact for the large scale circulation, atmospheric and ocean circulation, but there are hardly any observations to confirm these models or to at least evaluate these models. So we need to have an observational database to actually tell the models if they are wrong or right, or how wrong or how right they are. And to do this, we need targeted process studies to understand these processes. And we actually already secured ship time for one of these experiments in the summer of 2026, which I mentioned on one slide in the end again. Then I think the big question is how we can improve the existing model biases. And I mentioned models are getting into these very high resolution, into this very high resolution realm. But model observations don't keep up so fast. So we need to use these, we need to create observational findings, and we need to use them to evaluate these models, because they are getting better, they are getting higher result, but they need to be evaluated at these high resolutions. And this means that we need to more specifically validate and improve the parameterizations of these models. And I think one question that is always there is how we can distinguish between natural climate variability and global warming signals in our time series. And I think the very first step is, it sounds easy, but I think it's a huge challenge. We have to sustain our long-term observations just to monitor these emerging points. Try to have long time series to give these signals time to actually emerge from the noise or from the internal variability. Okay, so my strategy to do these things. I'm really much in favor, or I'm a fan of combining sustained observations with targeted process studies. I think there are many opportunities to use the existing system, but also to add on this. There are ships going out by NOAA, by GEOMA, every 1 or 2 years to the ocean, to the tropical Atlantic Ocean. So these are great platforms to add process studies to existing platforms. I'm also a fan of using innovative instrumentation. So in the process study that I'm going to mention in a few slides, we are trying to include a lot of different uncrewed vehicles, radar measurements, wire walkers. So I think this is an important step to actually advance our knowledge. And then we understood the importance of interdisciplinary approach for a very more comprehensive understanding of these processes, because we know how these BGC ejections impact the small scale processes. So I'm very much in favor of an interdisciplinary approach. I mentioned I want to build on existing collaborations with the NOAA Pirata program, with the GEOMA efforts. They are in charge of the Equatorial Atlantic mooring, so there are opportunities to collaborate with them on these cruises and on these platforms. And then of course also building new collaborations, and in particular hopefully during the next year when we actually do our process study, which was funded just earlier this year. So we secured ship time on board of the German Meteor. It's probably going to be the new one, because the old one is going to be retired early next year. And I'm a co-PI on this project. So I designed this experiment which shows you just a theoretical, or a typical August month in the North Equatorial region along these fronts of tropical instability waves. So we're planning to observe these processes along these fronts. We're trying to cross as many times as we can these fronts, and we include glider tracks, wave gliders, underways LED, X-band radar on the ships, but also hopefully even more. So I'm looking for collaborations with even more groups. Okay, and this is my summary. So I haven't mentioned it explicitly, but I'm a very much seagoing oceanographer. I've spent more than 430 days at sea, 12 major cruises, most recently as a co-chief scientist. I published 16 studies so far since I started in 2018, so 8 as a first and 8 as a co-author. I'm really interested in teaching. I just recently completed the Teaching Academy, which was a great experience. And I've been involved in student training cruises in Guioma, back in Germany, but also since I came here on the Walter Smith during the floats and cruises. I've built a network of worldwide collaborations in the US, Germany, also in France, Italy, and Cape Verde Islands. I'm interested in outreach activities, so I just started giving media interviews, guest blogs. I started being a panel member for the Clive Atlantic Region Panel and the Prada Scientific Steering Group, so I think these are also great platforms and great panels to represent the interest of the tropical Atlantic community. And just to mention, because I talked only about the Equatorial Atlantic today, I've also published papers on the AMOD, on Equatorial Pacific dynamics, and as well as a PhD on the subtropical Atlantic that I didn't mention almost at all today. But just to mention that there are more interest than just the Equatorial Atlantic. Okay, and with that, I'm finishing this talk, and I'm happy to take any questions that you might have. Thank you.
Thank you, Philip. That was a great talk. Are there any questions?
There's no question. I have no question. In your slide 17, you mentioned you have more number of hurricanes than the positive Atlantic Nino than the Nino 3.4. Slide number 17. Yeah. So, you mean like when we have Atlantic 3 Nino,
yeah,
you have more number of hurricane activity than the Nino 3.4. That means Atlantic Nino is very important than the Nino 3.4.
At least for this region, for the Eastern Atlantic region, yes.
Okay, yeah, this is very interesting because everybody think like Nino 3.4, like I'm talking about Pacific Nino is very important than the Atlantic. And this makes Atlantic Nino is also very important to understand.
Yeah. As far as I understand, the Nino index has more importance for Caribbean and Gulf of Mexico hurricanes, and this is just focusing on the Eastern Atlantic, where Atlantic 3 has been not really considered before that.
Thank you very much. On top of that, I have another question. You mentioned about a lot of observation. We also have the Argo floor.
Yeah.
So I'm thinking like what we are not getting from the Argo floor that we need to measure by going to see like you are doing. So what we are missing in the Argo floors?
I think the high frequency processes. Most of the Argo floats, they have they are set to do one profile every 10 days, right? And you have to be lucky that they are in the region that you want. That's what I mean with like targeted process studies. So of course there are a lot of observations, and maybe by chance one Argo float is in the same region that you want, that you have your process study on, but it's just by chance. And we had I know a few examples of when things were measured just by chance during a cruise, but then you don't really learn too much about it. You just see something interesting, but you have to come back and have to do a dedicated study to study these process studies, to study these small scale processes. And I think with Argo floats, it's I mentioned this one example where we kept the Argo float on the equator, but that's an exception, right? So most of the Argo floats, the big fleet, cannot be customized like this.
Thank you very much. Very nice talk.
Thanks.
Very nice talking here. Question on one of the slides you mentioned this banana eddies and
the banana shell eddy, yeah.
Right, and this ability of eddies or waves to maintain zonal currents.
Yeah.
And you're referring to the equator
Yeah.
specific, right? Just a comment that similar processes are observed at mid-latitudes as well.
Yeah.
Which is, it looks like a fundamental property of mesoscale of wave dynamics
Yeah.
to organize flows in zonal currents.
As far as I remember, this is based. Work by Greatbatch et al. and Richard Greatbatch, and we contributed the observational data. But as far as I remember him talking about it, he actually had this idea from the mid-latitude atmospheric processes where this banana shaped eddy plays a role, and then he applied this to the Equatorial Atlantic, where it actually also plays a role when you combine these mostly barotropic waves and how they interact with the zonal currents. So that was the nice thing about this study, that he actually applied this concept to the equator, and that we could help and provide the observational evidence for that. But yeah, that's right.
Great talk, Philip. You've done a lot of work.
Thanks.
I'm just interested in the kind of the relationship between the trends. So there's been a fairly strong trend in equatorial SST or regional SST, right? Punctuated, as you showed, by these really large La Nina events in the last few years. And then you've also had this trend in TIW activity, right? So
Yeah.
Are those directly related to each other, or do you understand that connection?
So the way that we calculate the tropic instability wave induced SST variability here is we're using the intraseasonal fluctuations of SST, right? So that's not necessarily connected to the trend, I would say. I know that from the Pacific Ocean, there's been a recent study where they also observed a huge increase of tropic instability wave activity, and they are attributing this more to increased gradients in SST, large-scale gradients, and then large-scale gradients also in the winds, and what's forcing then the currents and then the TWWs. We didn't extend that far to the generation mechanism of the trend. So we really just focus on, can we see something in the barotropic energy conversion term at these time scales. And yeah, I mentioned, we had some hypotheses, because we really expected, the whole reason for this is actually my NRC proposal. We know that some of these currents, they've been increasing over the last couple of years. We had a paper with Peter Brandt on the intensified EOC, for example. So I thought, if these currents increase, there must be more shear, there must be stronger instability waves. So we see an increase in instability waves, but we don't see a stronger shear. So the term in the barotropic energy conversion that increases is this high frequency fluctuation term. And we have some ideas what can cause this. We thought, for example, the currents there may be too close to just being unstable. So any increase in the currents just causes high frequency instabilities at the currents. It doesn't really increase the currents and the shear, but it causes the currents to be unstable and shed these high frequency current fluctuations. That could be one explanation. But there's also possibility of high frequency winds that can lead to more intensity and tropic instability waves. There was a model study by Franz 20 years ago. So yeah, I would say it's not completely clear, and we only did this from observations. But yeah, as I mentioned, bioclinic energy conversion is so hard to observe. You would need to have model studies, I think, to.
That's the thing I was going to ask you about, but it's kind of it's a bit of a paradox, right? So if the shear is really supposed to be responsible for the generation of the fluctuations.
Yeah,
the fluctuations are larger, but the shear isn't. So maybe it's the threshold instability. You're saying, like, as soon as the shear gets critical, you generate the TIWs, and that suppresses the shear, and you're kind of riding along that edge.
Yeah, and you don't see any change in the current or the shear itself. Yeah, that was our theory. So it's these two terms, right? So it must be one of these, and it's not the shear, so it must be the eddy term.
So is this region, you spend a lot of time focusing on this region, is it isolated from everything else? it's very complicated, but are there any remote connections? I'm wondering.
You mean the...
Remote, outside of this region, I don't know, maybe something coming from south and north and whatever.
Right, okay. So, it's in that kind of...
People talk about remote connections for the Pacific
yeah.
processes. And this should be much more, we know about AMOC and all that. Is it influenced slowly by other processes and somehow we see these things popping up differently?
Yeah, I think that's the point. I think it's these teleconnections, they are more active on... acid, atmospheric teleconnections, I'm not too sure that they are active on these mesoscale, small scale processes. Of course, I mentioned the Atlantic, how it's connected to the Pacific and the Indian Ocean, but of course, like you said, there's also the other way around connection to the Atlantic. So there's definitely, like I mentioned, impact of Pacific that can force equatorial waves, that can force Pacific, in the end, the Innu events, so these large scale distributions of heat or of temperature. I think, downscale, there could be an impact probably on tropical instability waves. But there could be something, But I haven't done research on that,
Sorry, curious about, you didn't mention much the Gulf of Guinea.
Yeah.
But I'm curious if you notice with your interannual variability any connection between the movement of the IPCC and waves and activity in the Gulf of Guinea.
I know, okay, I mentioned, do you have a good slide on this? So there's definitely like these equatorial cable waves. Once they hit the eastern boundary, they not only reflect back as Rossby waves into the interior ocean, but they also propagate north and southward as coastally trapped waves. So this has a huge impact on, for example, the Benguela-Niño region or the Benguela region, where similar heat events or heat waves develop. And they can also propagate northward. It's a little more complicated for the waves because it's easier. It's more north-south than over here. So usually what we see is that the coastally trapped waves, they propagate along the coast here in the Gulf of Guinea. But then right at the edge, most of them shed into the Atlantic again as Rossby waves. But there's very recently, people also came up with what they call the Dakar Niño.
Sorry?
The Dakar Niño, like the Senegal, capital of Senegal, in this Mauritanian upwelling system. There's also something like an interannual variation that they call the Dakar Niño. So, and they are trying to make connections now similar to how the Equatorial Atlantic impacts the Southern Atlantic, how it impacts the Gulf of Guinea and the upwelling system over there. So there's some wave pathway for both sides of the equator. Is that what you mean?
Yeah, I have been studying this area for different reasons, and the Gulf of Guinea is kind of very special, like the residence time is much longer, but you don't have a specific situation that to associate with, and I'm just curious about that region.
Yeah.
Thank you.
Yeah.
So you said Dakar?
Dakar, yeah, D-A-K-R-A.
Thank you. I will check.
R-A-R. D-A-K-A-R.
Any more questions? I have one comment.
Okay.
One question. Super interesting talk. I really enjoyed it. And I did some work in the Agulhas Current. It was 8 years ago now. And we also found that there wasn't intensification. We expected intensification because in the southern hemisphere, the intensification of the southern hemisphere westerlies, right, is pretty robust. And so there were a few papers saying, all the southern hemisphere western boundary currents will be intensifying.
Okay.
And so we looked for that in the Agulhas Current. We didn't find it, but we did find increased instability. So in a similar way that you found.
Yeah.
And then I had a second experiment where we put in some temperature and salinity measurements. And so we're looking now at baroclinic instability as well as the barotropic instability. And we have a few challenges because we don't have as many measurements as I would have liked in the upper water column. It's really difficult to get your moorings to stand upright, but it's really interesting as well that you see a lot of energy going back and forth between those modes without dissipation.
Oh, wow, okay.
You know, especially if you've got wave-like things going on.
Yeah.
So I think that's really fascinating to me too. You know, this question of like, okay, the ocean's warming, it's got more energy. Is that going into the mean?
Yeah.
The kinetic energy, you know, is that going to mean or fluctuations? And then this exchange between different modes of variability and different modes of energy in the ocean, and how that's all going to play out. I think it's really fascinating.
Right. Yeah. Yeah. Thanks. Yeah. That's interesting.
My other thing was a question,
Yeah.
which was, you know, maybe a little bit of a challenge for you, but so the you mentioned the warm biases in the models, and you know, we have a colleague here, Peter Zinema, who looks at low cloud over upwelling systems, right? And so this is connected with the Benguela, with the northern Benguela upwelling system. And I think that if she was in the room, she might say, why are you not thinking about those cloud processes and insulation in the eastern Atlantic over that system? Because I've seen papers saying that that's where potentially the cloud physics issue is where this warm anomaly comes from.
Yeah. Yeah, I mentioned the bias in terms of how these model studies suggest to improve it. So especially, I think it's this review paper by Seo that I mentioned, where they look at mesoscale acid action, and they really mention better resolving these small scale processes has not only an impact on the representation of the ocean circulation, but also on the atmospheric circulation. And I think that's maybe part of what you're saying, that atmospheric circulation and cloud coverage and distribution of coverage of clouds. Hopefully that also improves with a better understanding of just oceanic processes. But yeah, no, that's
a challenge. It's interesting. I mean, you're talking about, you know, going out on cruises and doing different things. You know, getting the moorings turned around at the same time as doing press experiments and everything. So maybe you also need to think about.
Oh, we do this. Yeah. No, I didn't mention. Yeah. No, we always include a lot of atmospheric measurements. We just in the last one we had LiDAR measurements, for example, for aerosols and for just vertical profiles of zonal winds. So no, we definitely, if we do this, or when we do this process study, we care about the whole boundary layer, or both sides of the ocean surface. Yeah, I didn't mention it. Thanks.
Actually, I have another question.
Sure.
You know, so from my experience in the quiche experiment further down here, we went to look at, you know, these scale processes, and Tamai probably has a lot to say about finding these scale processes too. Have you thought about how you will actually find them in the ocean? You know, because SSTs, often you don't have SSTs on that day because you've got cloud, and they're the only thing that really give you that scale. You know, with the SSH, you have phase problems because it only goes over every 10 days. Maybe you have some SWOT stuff there you can use. You know, I mean, it's tricky when you're out there at sea to find, and these processes are popping up, you know, and decaying on fast timescales. So, do you have any insights about that?
Yeah. So in the experiment design, I mentioned that we first of all, to get the overall or the large scale picture, of course, we rely on satellite pictures just to roughly identify the region of where the front is. But then on ship or on board, what really works well is these X-band radars. So they just, if there's enough wind, they measure the surface roughness and the surface currents, and you can really see these fronts nicely. And now the next generation of the X-band radars has an even higher range, so we have some heads up when we see these fronts. So that's probably the number one technique.
Are you going to have somebody with you on the ship that can extract that information in real time?
Yeah.
Okay, that's great.
At the moment, on the last cruise, there was it's sometimes even not necessary to have a person on there. It's just installed and it's part of the ship already, part of the default setup. So yeah, that's a really good technique. Yeah.
Yeah, very cool. Thank you. Any